Hello everyone. Again, this is continuation of notches and weirs, wherein we'll be putting an effort in understanding broad-crusted weir, ventilation of weirs, and then submerged weirs. This is the agenda of the session. We'll see one by one. This is our syllabus in which they have mentioned about broad-crusted, ventilation, and submerged weirs. Okay, we are going to see that theory in this session. Okay, broad-crusted weirs, what actually it means. Now, we have been showing the crust as a sharp crust here. Here, there is a sizable width for the wall, right? The width is shown as B here, and then the head over the crust is shown as H. Now, if you compare the size of H and B, we'll be able to classify the weir as sharp or narrow or broad crusted, and then the ranges in which the B and H should be so that they are called so is listed here. What is it now? If you want to call sharp crusted weir, the width B has to be less than 62.5% of H, means 0.625 H. So if you got a 1 meter height of the head, then this has to be less than, the width over here should be less than 62.5 centimeters, then we call it as sharp crusted. And if it is in the range of 0.625 H to 2.5 times H, then it's narrow crusted. If B is too large, more than 2.5 H, then it will become broad crusted. The typical character of broad crusted weir would be, if you look at the nappe, which goes that way, right, that sheet of water, right, has got no change in the height, but here in broad crusted weir it comes down, and then with some lesser head on the crust of the weir itself, it flows off. Okay, here if this is there, then the analysis is slightly different because of the practical observations, right? Anyway, from this what we can conclude is, if it is sharp crusted weir, the B has to be less than 0.625 H. You have to show this diagram. What you mean by B, what you mean by H has to be shown in a pictorial form, so that B is the width of the weir wall, and H is the head over the crust, and there is a sheet of water which is flowing, and we are comparing B with H. If B is less than 0.625 H, then it is sharp crusted. If it is in the range of 0.625 H to 2.5 H, then it is narrow crusted. If B is too large, like 2.5 times the head, then it will be broad crusted weir. Okay. Now here, if you compare the energy, that is H plus Z, the Z is over here, is equal to V2 squared by 2Z plus H plus Z. If they are comparing 1 and 2 here, so velocity V2 becomes root 2 G H minus H. Q theoretical is L into H, that is the cross-sectional area. The velocity is root 2 G H minus H. So Q actual will be equal to CD into Q theoretical. Okay, experiments prove that always this Q is maximum. Whatever discharge that is coming out of a broad crusted weir is maximum. So if this is so, then differentiate Q actual with respect to H, the variable over here, and then equate to 0 because it is maximum. So what happens here is the CD L root 2G, right, and then d by dh of h into root of h minus h. Now if you go on simplifying, you will end up with h equal to 2 into bracket h minus h. Okay, therefore h is equal to 2 by 3 times h. If you simplify this, right, 2h, then you got 2h, that comes 3h. So this lowercase letter h becomes 2 by 3 times capital H. Now if you substitute this h back into this equation, q actual will be equal to CD L root 2g. This expression becomes 2 by 3h, and multiplied by h minus h, and simplify, you will get 1.704 or 1.7, you can hold it as 1.7 CDL H raised to 3 by 2. So for broad crusted weir, always the discharge will be maximum, and then because of that the discharge expression becomes quite simple, and it is Q equal to 1.7 CDL H raised to 3 by 2. If you want to consider velocity of approach also, then it will be H plus HA raised to 3 by 2. That's it. Okay, that is about broad crusted weir. So points to be remembered as how to classify, and this particular thing, that experiments prove that always Q is maximum, hence the equation becomes quite simple. Okay, end contractions. Because of the streamlines, the flow from the edge jumps out slightly inwards as shown in figure, hence the effective cross-sectional area through the flow occurs is reduced. You know this now. Okay, that's how the end contraction. Already we have seen this. Anyway, here what I am talking about is ventilation of weirs. You can just have a look here. The sheet of water which comes over here, right? If I show you side view of this, it will be like this. Side view, right? If I this is submerged section, suppressed, in the sense that there are no end contractions. The length of the crust is equal to the width of the channel itself. The total width, there is a weir or a crust. Now if I allow, that was earlier length L, now this total becomes B, or length becomes B, H is the same H. Now if I allow the water to come, okay, when the discharge comes, it comes out as a sheet of water. Now when it comes as a sheet of water, now you can just see here that sheet and these walls, right, are closed, and here there is an air pocket that will be held in between, because when the sheet comes out, here there is a air, the sheet covers to the full width. You can just see here full width, and because of that what happens here is there will be air which is held in between. Okay, now when the flow continues, some of the air goes along with this sheet, so this free nappe which is flowing like that, because the air is gone, there will be suction pressure. This nappe is dragged inside, it comes inside, and more air goes, and this nappe is forced to cling to the weir wall itself. Then such condition is known as clinging nappe, right? Clinging nappe, or this is sucked nappe, this is free nappe. Now here when it is flowing like this, there is a suction pressure, more of water is discharged, and discharge given will not be same as that proved theoretically. Hence what is done is, here in the side walls on both the sides, of course, holes are driven. On the side view, how they look is this is the way how they look. Now what these holes provide is the free air that will be provided. Because of that, the nappe is free to fall off. Even if it sucks air, the air will be generously provided by these vents. This itself is known as ventilation of weir, right? Where the CD and the discharge calculation is not disturbed. Otherwise, the nappe will become clinging nappe and the discharge given will not be as given by the equation, right? Okay, submerged weir. What is submerged weir? If you observe here, there is a weir wall, the discharge is coming here, and with a head over the crust is capital H. But here on the downstream side, it is not falling off. The water on the other side is adding up, and because of that, it has also risen above the crust partially, and the flow is occurring. In such case, we call it as submerged weir or submerged flow condition. So what is that? When the water level on the downstream side of the weir is above the crust of the weir, then weir is said to be submerged. Below figure or the side figure shows a submerged weir. Okay, here. Now the total discharge is obtained by dividing the weir into two parts. Now what are the two parts? This red line has been drawn to bifurcate the two flows. The flow below is submerged weir, the flow above is free weir. Now whenever there is a rectangular notch, free weir discharge is 2 by 3 CD L root 2 G H raised to 3 by 2. But here H is this capital H, this lowercase letter h, minus if you do this height which is given by H minus H raised to 3 by 2. That is the discharge because of this. Now here also there is a discharge with a cross-sectional area of L into H. L into H cross-sectional area. CD the coefficient of discharge multiplied by root 2 G H minus H as the average head. Now the summation of these two will give you total discharge of submerged flow. So total discharge is obtained by dividing the weir into two parts, that is red line above this and then below this. Okay, so that makes submerged weir, and then calculation of discharge through submerged weir is given by that equation. I think with this we'll stop again. Stop here. Thank you.